I was always a curious kid, and my mom was actually a science teacher, and I loved to take things apart, but really I loved to understand how they worked. And what I've always wanted to do is understand how the planet works and how all the stuff around us works. I'm Josh Willis. I'm a climate scientist at NASA's Jet Propulsion Laboratory, and I study how the sea levels are rising. The satellites that I work on look back at the oceans. You simply bounce a radar wave off the surface of the ocean and you time how long it takes to go down and come back up every day for 30 years now. And we're able to chart how quickly the global sea levels are rising. And that tells us about human-caused climate change. The oceans absorb over 90% of the heat trapped by the greenhouse gases, and that causes them to expand. They also collect all of the water from the melting glaciers and ice sheets. It turns out there's enough ice in Greenland, if it all melted today, to raise sea levels by 25 feet. So Greenland is really a key to unlocking what's going to happen to sea level rise in the future. And our mission, Oceans Melting Greenland, was trying to figure out how much are the oceans melting away at the ice from below. But what we needed to know for OMG was what the oceans were doing down deep, way below the surface. And to figure that out, you have to drop a sensor. So we launched these little tubes out of the airplane, and when they got to the water, they would split into two parts. And one part would stay at the surface and radio data back to the airplane, and another part sank down through the water and measured the temperature and the saltiness as a function of depth. I remember one day we were flying along in these little DC-3 airplanes. They looked like something Indiana Jones would be flying around in. And the iceberg was so tall that it blotted out the sun. These things are hundreds of feet tall. The iceberg comes from ice that was on land that broke off. So it's a reminder of just how much ice Greenland is giving back to the oceans every year, which is key to understanding what it's going to do in the future. About 10 years ago now, about the time I started writing the proposal for OMG, I started taking improv classes. Sometimes I like to make funny videos, and occasionally I've been known to sing an Elvis song about climate change.
Sunny on Sunday, high 73. Monday rain was pouring down on me. Tuesday was cold, I almost froze my toes. But what's it gonna be next week? Who knows? That's weather.
I like to give people a little laugh to get them out of their seats and into the voting booths. The time scale of how fast the ocean reacts to climate change is very long. And it means that what we're doing right now is going to keep affecting our planet and our climate for generations. So we have a bigger responsibility than we even imagined. And I think that means that, we really owe it to future generations to start addressing this as soon as possible. Hey, everybody. Hello, how's it going? Thank you for coming out. In real life, this is sort of a, this is like my first in real life talk in as long as I can remember, it seems. So thank you for coming out and for being here. And if you're watching online, thank you too for being here. My name is Josh Willis, and I'm a climate scientist at the Jet Propulsion Laboratory right down the road from here in the Arroyo. A long time ago, we used to be on campus, and there's a whole story about why we're not anymore, but you can read that in the history books. But what I want to talk to you about is actually how I kind of went through my career studying the oceans and why they're so important for us, and what that has to do with our changing climate today. And so, hence my talk, Rising Tides, Tackling Sea Level Rise from Above and Below. And to me, this is a topic that's very close to my heart. The oceans cover more than 2/3 of our planet's surface, and they're rising. And if you think about that for a second, it's really startling, the idea that 2/3 of our planet is rising. We're literally changing the shape of the entire Earth with our changing climate. And to me, that's a very exciting topic to study. Of course, some people find it a little worrisome, as do I. But it's a great time to be a climate scientist, that's for sure. And I wanted to give you a little journey about what it was like for me to kind of come along and study these things and sort of what I've been doing lately. I'll start with this picture of me. That is on the launch pad at Vandenberg Air Force Base, or just near the launch pad at Vandenberg Air Force Base. And behind me, if I can get this to work, yeah, is a SpaceX rocket containing the Sentinel-6 Michael Freilich mission. Now, this mission was named after the previous NASA director for Earth Sciences. His name was Michael Freilich. And it's the first time NASA actually named an Earth science mission after a person in conjunction with the European Space Agency and EUMETSAT and NOAA. It's a mini partner mission. But it was a big deal for us because it was such an important mission. And so the Sentinel-6 Michael Freilich mission was launched in November, and it actually has, in November of 2020, I should say, but it actually has a very long pedigree. And before we launched Sentinel-6 to measure the oceans and how they change over time, there was a mission called Jason 3, and before that, a mission called Jason 2, and Jason 1, and Topex Poseidon. And these missions go all the way back to the early 90s, and they give us a record of how sea levels have changed everywhere on the planet once every 10 days for almost the last 30 years. And I was very lucky to have been working on these missions also when we launched Jason 3. Jason 3 launched in 2016, and it was launched on a SpaceX rocket. And I was fortunate enough to be working on the mission. I was at the press conference. And at the time, SpaceX was still trying to land these rockets back on the floating ship, the floating platforms. And this was one of their early attempts. And the media was sort of more excited about that than they were about the launch of the mission. So one of the reporters at the press conference asked me about it, and this was my response.
We'll take questions now, and we'll start right here in the front.
Can or will you guys care to comment on the launch vehicle?
I will say that we're excited to get a ride to space, and we hope SpaceX breaks a leg.
Oh, I can't say how satisfying it was to hear people in the audience groan when that happened. That was great. Yes, so the leg actually did break on that fateful day. It was a couple days after I said that. I was lucky enough also actually to go give a similar talk like this at SpaceX just recently. And the engineer who had to do the workup on that broken leg actually caught me afterwards and said, yeah, I had to go see Elon after that one. But he was aware of the video and still thought it was funny, so that was good for me. But anyway, we launched this mission in November of 2020, and this one was also exciting. I didn't say anything like that, like I did for the Jason 3 mission, quite, but I was actually able to be at near the launch site for the launch, and this one was exciting too because the rocket actually came back and landed at the launch pad. So normally the rocket goes up and it lands somewhere else, or it lands in the ocean. And they retrieve it, but this one was special because it actually came right back to where it took off. And it was very exciting, and I was able to take this little video of it. If you look really closely, right above the lamppost, you can see a little glow in the sky. That's the rocket actually coming back down. And as it comes back down, it's going faster than the speed of sound, so it makes a sonic boom when it's landing. And this was interesting because I was in a location where it went right behind the hill just before the sonic boom, and you can see it landing here. So that wasn't the rocket blowing up, just to be clear. That was the sonic boom, but I was a little nervous that I had gone 2 for 2, but fortunately that's not what happened. But one of the reasons I bring these things up is because I feel like, when we hear talks about climate change and how humans are impacting the globe, it can get a little heavy, and so I like to tell a few jokes here and there. So hopefully you'll have a few laughs along the ride here and a little bit of fun, and maybe learn a thing or two as well. So let's talk again about sea level rise. Now NASA has a bunch of different tools. NASA and its partners, I should say, have a bunch of different tools for measuring not just sea level rise, but what's causing sea level rise. And I'll get to some of that later, but first I want to show you this little animation, and we saw some of this in the opening video, about how we measure the rising oceans. So this is an animation of the Sentinel-6 satellite. Unfortunately, we don't have like spacecraft flying around that can take these kind of pictures, but we have really great animators, so we can see what they would kind of look like. And what this satellite does is it bounces this radar wave off of the ocean, and it measures simply how long it takes to go down and come back up. And that tells us how far away the ocean is, very precisely. And then if we also know the location of the satellite, we can actually subtract those two things and figure out how tall the water is. And if we do this again and again, this spacecraft takes one good measurement about once per second. Actually, now they're getting faster than that, and they can do higher along track resolution. But basically, we can get a nice map of the whole global ocean about once every 10 days from this satellite. And there's actually also a bunch of other satellites flying in different orbits that help us fill in the gaps a little bit as well. But together, these satellites give us this global picture of how the oceans are changing. And it's sort of like having a whole bunch of tide gauges everywhere in the world. And together they give us a really good sense of how the oceans have changed over the last 30 years. Now, I want to shift gears a little bit and talk about the changing of the climate. Of course, we know, I think most folks realize now that the planet is warming up. We live in a warming world. It's been warming pretty rapidly for the last 100 years or so. This is a plot showing the average temperature in the last 100 years, and you can see it rising. It's important to remember this is an average over the whole globe. So some places are warming faster, some places are warming slower, and so forth. But together, the entire globe is actually warming up. And this is happening very quickly compared to historic changes. We look kind of back in time, and we try and understand the reason for this warming. You can look at how the atmosphere has changed over the last 500,000 years. And we've gone through these cycles of warm and cold, and as we've gone through the warm and cold cycles, carbon dioxide has gone up and down about every 120,000 years. And this is a well-known phenomenon, and there's a whole bunch of things to explain it about how the Earth changes its orbit very slightly. But what's different is in the last 150, we've changed the composition of the atmosphere really radically and increased the amount of carbon dioxide by, we're going to be close to a factor of 2 before too long. So not quite yet, but we're getting close to being to where we're going to have doubled CO2. And that's a major change in the amount of carbon dioxide in the atmosphere. It's a global change, and it's one that's not going to go away for a long time. Now, people often ask, how do you know what the atmosphere was 500,000 years ago? There weren't scientists like you running around with instruments. And the answer is actually locked in the ice sheets, and other records too. But the ice sheets give us this really clear picture. Every year in places where you have ice sheets or glaciers, the snow accumulates, and not all of it melts in the summer. Some can melt in the summer sometimes, but not all of it melts. So then when the snow falls again the next winter, it forms these layers. And these layers trap little bits of the atmosphere, and you can actually go back in time and see what the atmosphere was like 500,000 years ago. And you can also figure out what the temperature was like 500,000 years ago by looking at the quantities of different kinds of gases in these little bubbles. So we can actually tell a lot about the past climate, and we know that what's going on today is very unusual compared to the last 500,000 years. Now, if we change the composition of the atmosphere, if we change what's in the air, then we change kind of how the climate works. So most of the energy for our climate comes from the sun, almost all of it. The energy from the sun comes in the form of visible light, which you know because you walked in here in the day. and it was very bright outside, and we're getting light from the sun right through the atmosphere. And the atmosphere is mostly transparent. It's mostly clear in terms of this light from the sun. So the light from the sun goes right through the atmosphere, and it warms the surface of the Earth. And then that warm surface of the Earth is sending energy back into space. But it's not quite the same. Some of it is reflected light, but a lot of it is actually what we call infrared radiation. And so this radiation is trying to get back out through the atmosphere, but it's not transparent to the atmosphere is not transparent to this outgoing radiation. So it gets stuck. It's trying to get out, and it gets stuck. And the more carbon dioxide in the atmosphere, the more it gets stuck. So when we change the composition of the atmosphere, we're changing the amount of energy that gets stuck on the planet. Now, the question is, what happens to that energy? And I know if you're online, you could write it in the chat right now, but if anybody wants to yell it out, anybody know where the energy goes? I'm just checking to see if you're awake. So far, you're failing. You're not awake yet. Wake up. I'm just kidding. No, you're doing great. Most of the energy winds up going into the oceans. Over 90% of the heat that we're trapping with greenhouse gases is actually warming the oceans. And we know this because we can count it. We've been measuring the temperature of the oceans. We measure the temperature of the air changing and how much water is in it. We measure how much ice is melting. And if you add up the energy from all those things, it breaks down like this. Almost all of it is going into the oceans. Now, that means the oceans are getting warmer, obviously, but it also means that they're getting bigger. Just the fact that the oceans are warming means that the water is actually expanding. And this is about 1/3 of modern day sea level rise. So we're heating up the oceans and we're making them grow bigger. And we're also, of course, warming up the atmosphere and melting ice. This is a picture of a glacier from Alaska, but you could take a similar pair of pictures from almost anywhere in the world. Over 90% of the glaciers in the world are in retreat. As the climate warms up, they melt more than they accumulate. They get more melt than they get snow. Or they have ice loss from breaking off at the end, which I'll talk about a little later. But basically, they're disappearing. And this one has retreated miles and miles back into this fjord since the picture in 1941. And if you went back today, almost 20 years later, you would see it's retreated even farther, maybe even around that corner. So we're watching these huge chunks of ice disappear. Of course, that water winds up in the oceans as well. And together, those two things, the melting of the glaciers and ice sheets and the warming of the oceans, cause the oceans to rise. And if we look at the record of ocean rise over the last 2,000 years, we see that the last 100 are very unusual. So a colleague that has been doing this kind of work for many years now, his name is Andy Kemp, he goes out into salt marshes and places like this, and he drills cores through the salt marsh. And by looking at the little critters that live in a very narrow range of the tidal zone, you can actually figure out the history of sea level along this coast and how sea level has changed. And if you look back 2,000 years, you see that sea level was pretty steady on the coast of North Carolina for about 2,000 years. You had a little bit of sea level rise during what's called the medieval warm period. After about 1500 or so, there was a little ice age, and there was maybe a little bit of a dip in sea level. But all that is really peanuts compared to the increase in sea level that you see at the very end of the record. And also, the blue on here is actually a tide gauge. So the red comes from the salt marsh cores, but the blue is actually a tide gauge. And you can see that the last 150 years have a rate of sea level rise that's totally unprecedented in the last 2,000. So we know also that the rise of the oceans is going faster than at any time in the last couple thousand years. So what does this have to do with NASA? Well, I mentioned at the beginning that this history of satellites goes back now almost 30 years. It started with a mission called Topex Poseidon. That's the satellite that got me my PhD back when I was at Scripps. And it's one that's really set kind of a gold standard for how we measure climate change from space. The reason is that its successor, Jason 1, was actually able to fly in tandem with Topex Poseidon for many months They flew one right behind the other about 30 seconds apart. And because they were so close together, they were measuring the same ocean through the same atmosphere at the same time. And we were able to calibrate them relative to each other very, very accurately. And we were lucky enough that Jason 1 lasted long enough to overlap in the same way with Jason 2, and Jason 2 with Jason 3, and now Jason 3 with Sentinel-6. And if you put all of those together, and you look at the rising tide of the globe for the last 30 years, it looks something like this. And each one of these on this plot represents one of the different satellites from that series of missions. And you can see the sea levels going up and down every year. So every year, there's this rise in sea level and then a drop in sea level. And this actually has to do with the exchange of water between the oceans and the land. So every year in the summertime, the atmosphere absorbs a bunch of, it evaporates a bunch of water out of the ocean. A lot of that falls as rain over land, and it takes time for that rain to run back off into the oceans. And because there's way more land in the northern hemisphere, this is locked in step with the changing seasons of the northern hemisphere. So in fact, this rise and fall of the sea levels that you see every year is sort of like the heartbeat of our planet. It's really this exchange of water between oceans and land that's been going on for time out of mind. So our satellites are so accurate, we can actually see the heartbeat of the planet. And on top of that heartbeat, we see this steady rise. Actually, it's not quite steady if you look really closely. That's not a straight line I drew through it. It's actually a curve. And the reason is that it actually fits better now to draw this curvy line instead of a straight one. And that's because the rate of rise is also increasing. If you look at the first 10 years, it's about 2 millimeters per year. The middle 10 years are about 3. The last 10 years is 4, and maybe even 4.5 millimeters per year. The rate of rise is increasing. So we're watching the oceans actually rise at a faster and faster rate, and we can do this because of this fantastic series of satellites, all connected one to the next, in an unbroken record of sea level change that lasts 30 years. And this is really important because sea level rise is actually one of the most easy to understand and comprehensive indicators of how much we're changing the climate. So the warming that we're causing by introducing this extra gas, the clearest effect it has is on the rising of the oceans. But it's also one of the most damaging impacts of human-caused climate change because so many people, hundreds of millions, live near the coasts. And as the oceans rise, structures are threatened, flooding rates increase dramatically, and sometimes all of a sudden, we think of this as a slow, steady rise, but in fact, if you're at the coast, it's not the slow, steady rise that gets you. It's the fact that this big storm or this high tide that you used to be safe from, now it's in your living room. And so this is an impact that's felt all around the planet, and it's a reminder that we all share the same planet, and the impacts of our actions are felt everywhere. So why do we need to measure it so bad? Well, as I'll talk about a little bit in the second part of the talk, we don't really have a good handle on how to predict how fast sea level rise is going to increase. These huge ice sheets at the poles in Greenland and in Antarctica are losing ice to the oceans, but they're not doing it in a simple way, and we aren't very good at predicting that yet. So in a lot of ways, these satellites actually give us our best prediction. So putting that curvy line through our record actually is a better prediction of the next 10 or 20 years than we can do by running a big fancy computer simulation of the ice and how it's changing. So our satellite altimeters, we call them, the Jason missions and now the Sentinel-6 missions, are really important for being sort of a yardstick for how fast we're changing the climate. Okay, so now I'm going to talk not just about sea level rise, but what causes sea level rise. There's another set of satellites called the GRACE missions, which are shown here, and these satellites are a pair that actually chase each other around the planet. So whenever one goes over something heavy, the pull of gravity causes it to speed up just a little bit. Then when the second one follows, it sort of catches up a little bit. They're actually named Tom and Jerry by some of them because they chase each other. Anyway, but what we do is we measure the distance between these very, very accurately. And by watching them move apart and together, we can actually weigh the land. And we can weigh things like the island of Greenland, which is covered in ice. And if we do that, we find out that Greenland is losing ice. So this satellite, GRACE, and its successor, GRACE Follow-On, have been measuring ice loss in Greenland since the early 2000s. And in that time, Greenland has lost more than 5 trillion tons of ice. So it's on Jenny Craig for sure. Now, what you can see on the left is actually that the ice being lost, these red patches, are actually focused not in the center of the ice sheet, but around the edges of the ice sheet. And this is important because this is where the ice actually comes into contact with the oceans. Now, remember, if you noticed at the beginning, I'm an oceanographer, so the oceans are going to come back in a big way in the second part of this talk. But if you were to, it's also a reminder, if you were to melt all the ice in Greenland today, it would raise sea levels by almost 25 feet. So this is one of the keys to understanding what the future sea level rise is going to be, because we are still trying to figure out how fast this is going to happen. And so that was really the genesis of this mission that we showed some nice videos from in the beginning, called Oceans Melting Greenland, or OMG for short. Yes, I did think up that name when I was in a comedy class, and much to the chagrin of some of my managers. But Oceans Melting Greenland turned out to be really the perfect name for this mission, because those 3 words tell you the science that we're doing: oceans melting Greenland. The oceans are literally melting away the ice around the edges of the ice sheet, and that's a big part of what's causing sea levels to rise. And most importantly, it's one of the biggest parts that we don't understand yet. So this effect of the oceans eating away at the ice from the edges is actually one of the things preventing us from making better predictions of future sea level. Now, I'm just going to show a quick little video to introduce OMG as a mission. There's enough ice here in Greenland to raise sea levels by 25 feet all the way around the world. It's an incredible amount of ice, and it's melting and adding to sea level rise. For Oceans Melting Greenland, what we really want to do is measure the oceans, measure the ice, and watch them change together year on year, and try and answer the question, how much are the oceans melting away the ice, as opposed to the air, which is what most people have studied so far. It's really a breathtaking landscape. These giant mountains and canyons are all along the coast. When you look out the window, you really get a sense of just how huge these glaciers are, these gigantic rivers of ice that are draining the ice out of Greenland into the ocean. And then they reach the ocean and it gets all broken and craggy and big chunks fall off. It's incredibly dramatic. Kulisuk is just a tiny little town in southeast Greenland, and we've been launching probes out of here for the past 4 or 5 days. It's already been a fantastic year for OMG measuring the oceans. We launch them right out of this tube right over here. Open up the tube, you can look right down it and see the water passing by, or sometimes the icebergs or clouds or whatever it is we're flying over. We slow down a little bit and we just push these big gray cylinders out of the bottom of the plane, and they fall to the ocean and measure the temperature and salinity when they get there and radio it back to the plane. We're really trying to look at the ice and ocean all the way around Greenland. So we're dropping 250 profilers. We're going to cover the coastline all the way around. And in the spring, we map out the glaciers with a radar, also all the way around. So we're really looking at mapping all of the ocean-ice interactions in Greenland as best we can with one mission. Yeah, so there's a little introduction to OMG. I should start by saying, actually, that OMG has now concluded. So this was from the start of the proposal to the end was almost 10 years of my life. That was a very remarkable and incredible journey. But the idea was to do a big experiment using airplanes to see if we could try and make some sense of how the ocean might be affecting the ice loss in Greenland. And it was quite a journey. In the last couple years, we had to do it during COVID, which was a huge challenge. But we were actually able to get to Greenland every year for the past 6 years and collect this really unprecedented set of temperature measurements of the oceans around the edges of Greenland and really watch how it affected the ice at the edges. And the basic idea for OMG was, as I said in the video, to measure how the ocean temperatures were changing as comprehensively as we could from one year to the next, and then also to measure the ice itself. So we had another airplane that actually flew a radar that measured the ice edge and looked for how much it thinned and retreated, or in some cases, how much it actually grew, which I'll talk about in a second. And what we found was that if we looked at the ocean temperatures, they were a really good predictor for what the local glaciers were going to do. So we essentially were able to confirm this hypothesis that the oceans were playing a huge role in melting away the ice from the edges. And this next little video shows you sort of how that works. This is an animation of a glacier. And in the summertime in Greenland, when the glaciers start to melt, the water collects at the surface and forms these pools. And the pools will actually melt all the way down through the glacier and deposit the water underneath the glacier on the bedrock below. Then the water flows out underneath the glacier, and eventually it reaches the ocean. Now, the glacier water, the melt water, is very fresh and very light, and the ocean water is warm and salty. So as the glacier meltwater reaches the ocean, it tends to rise up the face because it's not coming out right at the surface of the ocean. You can see it's actually coming out at the bottom. And as it rises up the face, it pulls in the local water, which is often warm at depth, and eats away at the bottom of the glacier. If it does this long enough, then a huge chunk of the glacier will break off in a process called calving. If the calving happens fast enough, the glacier itself will retreat. And as the glacier retreats, it speeds up because there's less friction around the edges holding it back. So this entire process allows the glaciers to speed up in the presence of these plumes that come up from underneath. But it's really the way the plumes interact with the local water that's the most important thing. And if you look at the waters around Greenland, you'll find this really interesting thing where the water is what I call upside down. You have a layer of cold water at the surface and a layer of warm water down beneath that. And the reason for this is that the cold water actually comes from the Arctic, which is the freshest ocean in the world. The warm water comes from the Atlantic Ocean, which is the saltiest ocean in the world. So the difference in saltiness is actually what causes the warm water to be below the cold water. Now, this is a problem for us at NASA because what we like to do is look at things from space. But there's not a good way, maybe somebody here can figure one out, but there's not a good way to measure the temperature hundreds of meters below the surface of the ocean from space. So what you have to do is put these little thermometers on wires down there, which is what we did for many years throughout OMG. Now, we had a bunch of different surveys. We drove ships around to measure the sea floor. We flew other airplanes to also tell us about the gravity, which also tells you about the sea floor. But the two big surveys were really the ice survey, which I mentioned before, and all these little red stripes are places we flew an airplane and measured the ice edge and how it was changing over time. And then all of these little yellow dots are places where we dropped one of those sensors from the plane and collected information about the temperature, not just at the surface, but all the way down to the sea floor there on the shelf. So about 250 times a year, we would collect these temperature measurements, and it gave us a really amazing look at how the ocean temperatures were changing. Now, sometimes it was very dramatic, like when we would fly over a glacier in the far north called Petermann. This is a glacier that has a large ice tongue. that's floating, and so it's a long, flat area. And somewhere during our time there, a large crack opened up in Petermann, and so we decided to see if we could deposit one of our temperature sensors into the crack. Now, this is a little video I took out the window when we were doing this. I just want to say we weren't really flying this fast. It's a time lapse, so don't be alarmed. It was very safe. But here we go. This is us flying over the ice, and way off in the distance, there's a little dark patch of water right there, and that's where we were actually able to drop the probe. Now, unfortunately, that one didn't work because it turns out that the water there is very fresh, and the probes we had at the time needed salt water to activate. But nevertheless, we showed that you could accurately drop one there, and you could collect data from an airplane in a place like the Petermann Glacier, which was a really exciting thing to do. Won't make you watch it again. So we also saw things like in that animation. So in the animation, it showed the plume of water coming up the face, rising up the face, and occasionally these plumes are so strong that they make it all the way to the surface. And this is one of those plumes on a glacier in northeast Greenland that we were able to see. I believe this was in 2020. And in this one, it's so strong that it's bringing up water from below. The water also has mud and stuff in it because it's been running along the underside of the glacier. So you see this big brown pool. And if you look really closely, or if you zoom in on YouTube or whatever, you can see that the surface is actually roiling because this water is coming up so quickly. We collected a temperature and salinity profile in this one and in many others as well. And it was this kind of really extraordinary data set we were able to collect. These things are only open for a day or two, so we really had to get lucky to fly over them and see them. And in our last year, we actually we got lucky again, and we flew over one plume at a big glacier called Helheim on the east coast of Greenland. And this was sort of a big deal because before we went, there were no reports that the plume had opened up the water next to the face of the glacier. All I had to go on, that there might be a plume there, was this little green dot that you can see on the left side in a satellite image that was taken the day before we flew. So I saw this satellite image the night before, and I said, we should go try to get that plume. So we flew all the way across the ice sheet, and we got there, and we were lucky enough to see this plume and measure it. So again, it was a really exciting time. Here, just to prove it was exciting, this is another image of us flying past an iceberg. There was one in the opening video too. But these were really these enormous chunks of ice that we got to see up close from the air. And it's a reminder just how much ice is being dumped off the ice sheet by these glaciers. So we think of the glacier melting in a warming climate as just the air gets warmer and it melts the glacier from above. But in fact, the glaciers are dumping these huge chunks of ice into the water all the time. And when you fly past one like this and see how big it is, and remember the fact that 90% of it is below the surface, you get a sense for just how huge the ice is, how much ice is actually coming off of this ice sheet into the oceans. And so it was a really eye-opening experience as well. Now, one of the things that I'll just touch on really briefly, and then I'll wrap up so we can talk, is in the first couple years of the mission, we actually found that there was one glacier in Greenland, one really big important glacier in Greenland, that was growing. And it was, I'll get there. It was a glacier called Jakobshavn, known locally as the Ilulissat Glacier. And this is an image taken from our radar data where we flew the airplane over it. And it's the difference between two different years. So in the top, it's 2016 and 2017, the change from 2017 and 18, and then 18 and 19. And the blue areas are places that the glacier is getting thicker. It's actually growing. And this was a huge surprise. This glacier had been retreating and shrinking for 20 years steadily. So when we started to see it grow, the biggest glacier in Greenland, the planet's warming, everything's warming, why is it growing? It was really a huge shock. And we were actually able to pin down the reason why. And the reason why is that the ocean temperatures actually cooled offshore from the glacier in the first couple of years of OMG. And this is one of the few places where we have records that go back a couple of decades. And what you can see in that panel There's temperature as a function of time on this axis and depth going down, and the color brightness is the temperature. It's sort of red and warm in the 2000s, and then in 2016, it cooled really rapidly. And this actually coincided perfectly with the growth of the glacier. Now, since then, it's warmed up a little bit. The glaciers started retreating. Whenever it warms or cools a little bit, the glacier reacts very quickly. Now, this cooling is part of a natural cycle that comes out of the Atlantic Ocean. There have been cool periods before, and there'll be warm periods that follow this. But this warm and cool change is actually what allowed us to say that the glacier was responding in a really big and powerful way to what the ocean temperature was doing. So in a lot of ways, this was what really helped us confirm that the oceans are playing such a huge role. And then there was a really great paper by a postdoc now at JPL called Mike Wood, and he showed that actually this effect encompasses the whole ice sheet. So using a model to kind of go back in time a little bit with the temperature data and satellite data to look at the retreat of the glaciers, he found that in fact, whenever the oceans warmed, the glaciers sped up, dumped more ice into the ocean, and when they cooled, the glaciers actually slowed down. And so as the oceans warm and cool, the whole ice sheet is literally speeding up and slowing down and evacuating more or less ice into the oceans. And this is critical because if we want to predict how Greenland is going to evolve in the future, we really have to measure the oceans to see how fast they're warming if we want to know what's going to happen in the future. Now, that's sort of enough about OMG. If you want to find out more, the OMG webpage is omg.jpl.nasa.gov. Check it out. There's some fun videos and other stuff on there. Before I do questions, though, I do want to leave you with one last final thought. So as I've kind of gone through this journey of discovering what my career was going to be like and learning about the oceans and ice, I've always tried to kind of keep a light heart about it and to have a little bit of fun. So I'm going to show you one more video that's just a video of me having fun. I hope you'll have fun too, and after that, I'll answer some questions. So I'll be right back.
Hello there, little lady.
Say, what's climate?
Well, you curious little ankle biter. Climate is the generally prevailing weather conditions, including temperature, precipitation, humidity, wind, cloudiness, as a function of time throughout the year, composited over many years.
What?
Let me try something a little different.
Sunny on Sunday, high 73. Monday, rain was pouring down on me. Tuesday was cold, I almost froze my toes. But what's it gonna be next week? Who knows? That's weather. Oh, that's the weather you got. But you take a bunch of weather and you average it together and you're doing the climate right.
There you go. All right. Thank you very much. That's my Elvis impersonation. Don't trust me, go see the movie. He's way better at it, but I will take questions. If you'd like to see the rest of that video, Google Climate Elvis. If you'd like to know more about OMG, well, Google OMG, but you won't get me, all right? And let's answer some questions. Cool. I know, everyone's asleep now. Yes, there is a microphone right up here. If you don't mind getting up and talking to the microphone, then the people out there on the internet can hear you too.
Thank you, Elvis. Appreciate that. That was great.
Thank
so
you.
10 years and what's next?
What's next? That's a great question. I'm planning to see if I can find an agent and do some more Climate Elvis gigs. But no, I think part of what's next is to really do a similar mission like this in Antarctica. Now, probably it won't be Climate Elvis down there, but I hope it'll be somebody, because Antarctica actually has enough ice to raise sea levels by much higher, much more quickly, and it's even more influenced by the ocean than Greenland is, because there's less, the atmosphere there is colder, so there's less air warming that's important. So the oceans melting Antarctica is hopefully something that's coming soon. I'm going to switch this. really quick. Yes, and we had another one right down here. I know there'll be some online, so I'm getting a little thing up. Yes, go for it.
With the increasing improvement with drones, do you think that the use of drones will be able to replace flying in the D series?
That's a great question. Yeah, could you use drones to do this? Well, I hope so. There are drones that can actually launch something off the drone. We still have this problem where we have to go to the ocean and measure it directly because the water temperature that we care about starts 200 meters, like 600 feet below the surface. So you really have to have something in the water to measure it, and that's what we need. Could drones do it? Possibly. I think they weren't quite ready when we set out to do OMG, but a lot's happened since then. Yes, one more.
Hello. I'm not a scientist, but I would like to know, so hypothetically, let's say the whole planet turns into water, like we keep melting and melting and melting.
Waterworld, the movie by Kevin Costner, right?
Yeah,
Yes.
and what, do you know, because you're a scientist, like can planet exist in water shape, or are we like gonna like drown? I mean, I don't know, are we gonna still be in space, or are we gonna just, I don't know, be everywhere? Like what's the worst case scenario?
Yeah, how
like
much?
a million years from now, you know?
Yeah, that's a great question. How much water can there be? How much melting can we get? Well, if you add up all the water that's locked away in ice right now, it's 100 meters or so, I think, something like that. So a few hundred feet of sea level rise. So we're well above 300 feet here in Caltech, and a whole lot of the land is. So the land wouldn't disappear entirely. But a rise of even 1 foot or a small fraction of a meter would really be devastating around the planet. So you start to get huge impacts with just a foot or two of sea level rise, long before you get to these scenarios where everything is melting. So could we have a water world? There doesn't seem to be quite enough water, but we're going to be in trouble long before then. Yes. Yes, we'll go over here, and then I'll take one online. Yeah, go for it.
How do you account in your future calculations for astronomical inconsistencies, for example, the tilt change of the Earth, the precession, the distance between the Earth and the Moon, and so forth?
Yeah, that's a great question. So if you look back in time at the history of climate change, we go through these cycles that last 120,000 years or so. And so all that stuff is still happening, the change in the tilt of the Earth, as you said, and the distance and all these other orbital parameters. The thing is that those tend to change, they tend to take 1,000 years or more to change. And the changes that we're seeing happen in 100 years. In fact, right now they're happening every 10 years. I would say pretty much every decade brings a new climate that we have to adapt to. Every decade is warmer than the last. Every decade, sea level rise is substantially higher than the last. And actually now, every decade, the rate of sea level rise is increasing. So the changes that we're seeing are happening so fast that they're really dwarfing anything that could be happening with the astronomical changes. Now, people still continue to calculate these. It's still interesting. We're still part of the equation. We certainly care about the tilt of the Earth, and all that stuff is measured. But the changes that we're causing are just so much faster and so much larger than those that they're not having a major impact. So I know there's a couple more questions out here, but I want to take a couple off the live stream. So we have Nicola asks, do you have a prediction about how long it will take to melt all the ice on Greenland? Well, that's the $64,000 question, as they say, as old people like me say. How fast will Greenland melt? Now, the assumption is that it would take hundreds or even 1,000 years to melt all of Greenland. But that assumption is largely built on the idea that it's melting from above. So if you add in the melting from below and the breaking off at the edges, the answer is right now a big question mark. And pretty much every time we make a discovery about how fast Greenland is losing ice, we raise our predictions of how fast Greenland will lose ice. So the short answer is we don't know, but that's actually in some ways more alarming than whatever the real answer probably is. So let's go back to in person. I want to reward you all for coming in real life, but we'll get back to these. Yes?
Hi, thank you for the talk. I really enjoyed it. So quick question. I think you were talking about the Jakobshavn. I'm sorry if I'm pronouncing it wrong.
Yes, Jakobshavn.
But you said that it was growing constantly, but in the 3 graphs that you'd mentioned, I could see that the blue, which was essentially showing the density of the glaciers themselves, was decreasing, even though the area was increasing. So is there any specific reason for that?
Yes, you have a very sharp eye. So Jakobshavn is the way that Westerners name the glacier. Ilulissat is what the locals call it. And you're absolutely right. The rate of rise, the biggest happened between 2016 and 2017. And then the rate of thickening, we'll say, got a little slower, but it spread out over a larger area. And so this is the glacier sort of reacting to whatever happened at the front. And what happened at the front was the glacier actually advanced. It moved forward by about 4 kilometers, even though it had been retreating pretty steadily for most of the last 20 years. And it moves around a little bit, naturally as different things change, as the different amounts of that subglacial runoff happen. So different amounts of melt mean different strength of plume, and that can actually have a little bit of effect from year to year. But the biggest factor in what determines whether it's moving forward or backward still seems to be the water temperature there. And we accounted for all those things, as many as we could think of, but really the water temperature explains most of what's happening. So that was a big confirmation of what we thought was going to happen with OMG, was that the oceans are really important. But yes, there's always more to the story.
Thank you so much.
Thank you for the question. I'm going to take one more online. Saiko, I hope I pronounced that as close as possible, asks, is there a localized area where the rise of the ocean is more significant than the average shown in the diagram? Yes, what a great question. I feel like I'm doing my departmental exam again. This is great. Yes, absolutely. The ocean isn't rising the same everywhere. And in fact, actually, there are some places where the rise is much more quick. There are other places where the rise is slower. So that global number is really an average over the whole world. But especially with a 30-year record, you can see that some places are 2 or 3 times faster and some places are 2 or 3 times slower. And this has to do mostly with the ocean kind of changing its currents and moving heat around. But also a little bit it has to do with where the rise is coming from. So when ice melts in Greenland, it actually changes the gravity of the Earth and the tilt of the Earth a little bit, and that rearranges the sea level a bit. It's a very small effect, but it's something we're beginning to be able to measure. So yes, sea level rise is not the same everywhere. But if you're talking, especially when you're talking about centimeters of sea level rise over the course of 20 or 30 years. But when you start looking out into the future, if you start thinking about 50 years from now or by 2100, then actually the rate is going to be very uniform, much more uniform than this, and a foot is going to be kind of a foot everywhere. Maybe it'll be 1.5 feet over here and 3/4 of a foot over there, but everywhere is going to get a whole lot more. So excellent question. Yes, okay, let's come back here.
Yeah, you mentioned studying the ice in Greenland and then another possible exploration in Antarctica. Is the Arctic ice also worth considering, or no? Is that just too big and too small?
Oh, that's a great question. What about the Arctic ice? The Arctic ice is super important, but it plays a different role than the ice on land. The Arctic ice is actually floating ice, so it's ice that sits on the Arctic Ocean, and it's made by freezing seawater. So it gets cold in the winter, and the ocean itself gets so cold it freezes sort of from the top down. Now, this ice is not nearly there's not as much volume as there is in Greenland, but the main thing is that ice is already floating. So if that ice melts, it doesn't directly cause sea level rise. That said, it's really important for the climate of the Arctic. So as the ice retreats, the water, open water is left behind. That could absorb more sunlight, which changes its temperature more quickly. It also can evaporate water. part of the reason the Arctic is so fresh is that the sea ice is like a cap keeping the water from evaporating out. So that water vapor changes the local climate as well. And those feedbacks actually cause the Arctic to be warming up much faster than anywhere else on the planet. So the Arctic ice is super important for the warming. It just doesn't cause the oceans themselves to rise.
Thanks.
You bet. Thank you. Cool. And yes, we'll do one more, and then I'll go back and forth.
Thank you for the talk. I was just curious, it seems like you're talking about the ocean being one of the primary source of warming of this ice, and you're dropping these probes, so I'm thinking like one major variable is probably the surface area of ice under the water, and like how is it that you determine what the surface area of the ice is against the ocean?
That's a great question. So how much ice is really touching the water? That's what it boils down to. And one of the first things we did with OMG was we drove a ship around in and out of all the fjords, and we measured the depth of the sea floor. And the reason we did that was in part because that warm water, that sits down below, it has to reach the glaciers. So if it goes over a speed bump or something, it might get slowed down a little bit. But it was also to get close to the glaciers and measure how deep the water was right next to the glacier. And that's important because it tells us how big that face is, right? The fjords tend to come down like this and then tend to be pretty flat along the bottom. So we know pretty well how wide it is, but in a lot of these places, we didn't know how deep the glaciers were. And almost everywhere we went with the ship, we found out, oh, they were deeper than we thought. So there was more water exposed to the oceans than we figured. And some of them have a face that's 800 or 900 meters deep below the water. So you see 100 meters or something out of the water, but there's almost 10 times. Not quite 10 times because it's not floating, but there's almost 10 times as much below the water. So imagining as you fly over these things, you see this giant ice wall, imagining that it's many times deeper below the surface than above is really startling. And you're absolutely right. The deeper they are, the more they feel the water and the more vulnerable they are to the warming of the oceans. I'm going to take one more online. Son Ben asks, how long do the sensors that were dropped out of the airplane keep on working? If their batteries last a long time and they don't move, can they yield longitudinal temperature and salinity data? Oh, longitudinal, I like the big words. Yes, so most of the sensors, the 250 per year that we dropped, actually only take one profile. So they have a very small battery. They're really expendable probes. And we did this because at the time they were really the best technology. And we wanted to make sure that we got the probe right where we wanted it. We got the location of the profile right where we wanted it. And without being in a ship, that can be very difficult. However, in the later years, we started deploying a few instruments that instead of just collecting one profile, they can actually survive for a couple hundred profiles and can live through the winter. And so for these, what we call floats, they're modeled on floats used by the Argo array of floats, which is a global observing system of floats. These floats actually can dive down, sit on the bottom for a few days, come back up, take a profile and send the data back to us. And with these, we've actually been able to treat them almost like what oceanographers call the mooring, where they park on the bottom, they stay pretty much in the same place, and they tell us a time series. They tell us over time how temperatures and salinities are changing. So the future, after OMG, will probably be finding a way to put these floats around the edges of Greenland to monitor for the long term. Yes?
Thank you so much for coming here, first of all, and I liked you. You're a great Elvis, too.
Oh, thank you. Thank you very much.
As someone who has scientific authority that I would trust, what do you suggest to those of us who aren't scientists and don't have the money to influence policy do with our own individual responsibility to help fight this if we can do anything?
That's a great question. Well, I would say you actually do have the influence to make a difference. Vote. Talk to your policymakers. We have actually a bunch of policymakers that represent us, right? We have city council members, we have state representatives, we have Congress people, all the way up. And letting them know what's important to you is kind of part of our responsibility as good citizens, right? It doesn't even have to cost, more than an email or a phone call. Those things are actually important. Of course, voting is really important, and trying to make your voice heard is really important. In some ways, at this point, for doing something about climate change, that's almost more important than what I'm doing, right? I'm the harbinger of bad news. I'm telling you that the planet's changing, that we need to do something about it. But it's really up to all of us to figure out a way through it together as a society. And so speak up. That's the most important thing you can do. And also, don't be discouraged. You do have a voice, and you should use it. Yes. Yes.
Okay, so you talked a lot about how if all of the ice in Greenland melted, the oceans would rise by 25 feet, right? So I was wondering how you got that number with all, everything you have to take into consideration, with the oceans expanding. How do you get that number?
What a great question. How do we know how much ice is in Greenland? At the beginning of OMG, we knew less than we do now, actually. We're still learning about the bottom of the ice sheet. So we can measure the height of the ice sheet really well, but how deep is the ice sheet? So there are planes with radars that have flown over it, and they can go all the way through the ice and bounce off the bedrock and tell us how deep it is. Occasionally, people drill a hole all the way down, but that's really hard to do. We also have measurements of the gravity over the ice. That's important because, if you have a little mountain underneath the ice, then if you fly a plane over it, the pull of gravity gets a little strong over the mountain, and you can figure out the depth a little bit. So we put all that stuff together, and then the other thing is the ice tells us how deep it is. So it turns out that if you know the speed of the ice, which we actually know really well from satellites, you can kind of back out how deep the ice is. So let's say we have think of the ice like going through a tube in one of these glaciers. We know how fast it's going, and we took a measurement over here of how deep it was, so we know how much ice is going through that tube. Well, as we watch it speed up or get thicker or thinner, then you can kind of back out what the bottom is like. And so there's a scientist named Matthew Morligam who's been putting together this thing called Bed Machine, and you can Google Bed Machine Greenland and you'll find it. And it has this amazing map of what the underside of the ice looks like. And so you can see actually that it's fascinating. Some places have been measured, some places are kind of guessed at by this ice flow. But you can actually see that the middle of Greenland sits below sea level. So in fact, actually, a huge chunk of the ice sheet is resting below modern day sea level and is vulnerable to this retreat from the edges. But that was probably more than you wanted to know. But thank you very much for the question.
Yeah, thank you.
You bet. There's one more online, if everybody wants to stick around for 30 seconds. Steve Ladoci, I know you. Thank you for asking this question. He says, great talk, Elvis. How is the Greenland ice melting impacting the thermohaline circulation, or overturning circulation in the North Atlantic? If I'd have known I had to give a whole nother lecture, I would have waited on this question. Now, the overturning circulation is a part of the ocean circulation in the Atlantic where warm water goes north in the Atlantic. It sinks in the far North Atlantic, and then it returns to the south. And so after sinking, it's usually really cool. So you have this cold water going south, you have warm water going north. That means the ocean is carrying heat into the Northern Atlantic. And this heat actually winds up in the atmosphere, and it actually affects the climate all around Northern Europe, the climate of Greenland itself, around our east coast. All of it is affected by the oceans carrying this heat. And there's an idea that if Greenland loses enough water, enough ice, then a layer of fresh water will form over the surface of the North Atlantic and stop that sinking and turn off this overturning circulation. This was actually the plot of the movie The Day After Tomorrow. Dennis Quaid, you're all too young to know who he is. Well, maybe some of you aren't. But anyway, this is what this movie was about, the overturning circulation shutting down. It caused climate disruption. And so that is probably something that is in the future, is a slowing down of the overturning circulation. but it won't have the kind of craziness that was in the movie. It will affect the regional climate. It can change the storm track. It can affect how quickly things warm. But still, global warming is going to be bigger. So there'll be some impact from the changing of the overturning circulation, but it's still going to warm up. I think that's all the time I have. If you want, anybody who's here in real life, sorry, people online, you can come up and get a sticker for OMG. I have these down here at the bottom of the stage. Thank you all for coming. It was a pleasure to be here, and drive safe getting home.